Welcome to lecture 4. So happy to see you again, happy to see you back. I hope you are following the course without problems. So, as you know, lecture 3 was really a lecture about recalling some concepts, some definitions. So maybe you were already familiar with them. So, if you skipped that lecture, it was fine, no problem. Really, this is like the continuation of lecture 2. But the point is that now we are going to define, finally, height in general, so for abelian varieties. So actually for varieties in general and in particular for abelian varieties. So it's a little bit of a generalization of what we saw in lecture 2. Okay, so this is weird. I would love to have you in front of me so I could see your faces and I could see if you are really following the course, if you are understanding. So, this is a new experience for you and for me. So I hope you are following the course in a nice way. And of course, please, if you have questions, ask. So you have the chat in the online platform, so really don't hesitate. Ask me questions about the lecture, about the exercises, about whatever you want, okay? Okay, so let's start. Okay, so as every day I'm going to mention which ones are the references that I'm following today. So again, in case you want to see things, the same things said in a different way, okay? Or if you just want to go back, so of course you can look at my notes, but you can also look at the main references. So here we have the book by Andri and Silverman. So today we are following sections B3, 4, and 5. So, of course, this is a lot, right? Because this is 3 sections. So I'm not really saying everything that is in the sections, but what I mean by that is like everything I'm saying today, you can find it in here, okay? And if you prefer the other reference, the one by Bombieri, then you can go to section 9. So again, actually it's not that I'm telling things from here and from here, is that actually you can find everything about the Néron-Tate height. So this is like a classical concept, so you can find many references. So you can follow this book if you like it more, or you can follow this one if you prefer this one, as you wish. Okay, so let's start with the first definition. So, definition. Let phi from B to Pn. So this time B is a variety, so we have a morphism, B a morphism. So we are going to define the height on the variety V by using this morphism, because we know now how to define the height on a projective space, right? That was lecture 2. That we know how to do it. And we are going to use that definition to define a height now on any variety. But the ingredient that we know to be able to do that is a morphism. So somehow we need to be able to see our variety inside Pn. But this is kind of natural, right? Basically what you are doing here just is like choosing coordinates, let's say. So if you want, you just can think about phi. You can take any phi, but you can take, for instance, like the natural inclusion of the variety into a projective space. That again, this is just done by choosing coordinates of the variety. So this is not difficult to take, given a variety. Okay, so now we are going to define the height on the variety V relative to the morphism phi as follows. So the height for a point P in the variety P relative to the morphism phi is defined as the height, as the height of the image of the point. Okay? So, I guess that this is the natural thing to do, right? If we know how to define a height in here, so the idea, I want to define a height for the points in here by using this morphism. So the idea is that I use the morphism to see the point here in here, and then I associate to this point the height that corresponds to the image of the point in the projective space. That this is something that we know how to do, right? Okay, very well. So we give this definition, but now, of course, we want to study the properties of this height that we have defined. So theorem, we'll see those properties. And I mean, actually, this theorem has a funny name. It is called Veil height machine. And I mean, this funny name, you will see why. So the idea is that we're going to see how now, given a variety, we can define many different heights. So I mean, this is why this is called, the idea is by Veil, so this is why the name. And why height machine? Because I mean, this strategy, this idea by Veil, allows you to produce many heights on your variety. So of course, later on, we are going to choose the height that we like the most, or I mean, we are going to study like the different properties, the different heights that we are going to produce with this machine, how they are related, okay? And I mean, how we can read information about the variety by looking at the value of the height. Okay, so this theorem says the following. Let K be a number field. So, I mean, again, this could be stated for more general fields, but I mean, for us, it's okay with number fields. So, I mean, we are working in this case, and I mean, this is the case we are going to use all the time. Yeah. So now, for every smooth projective variety B defined over K, there is a map. So before writing down the map, so the map is going to be the height machine, so how to produce all this height associated to the variety. Let me say something. So, I mean, I said that here K is a number field. Actually, it could be more general, but we are working with number fields, so okay. And then for the variety, I'm asking B to be a smooth projective. Actually, we could work and we could do the same thing for varieties with singularities, but I mean, it means that then I would have to state like many exceptions in the properties that I'm going to state in the theorem. So, I mean, it's easier if I just state it for smooth projective varieties, and actually all the examples that we are going to see, they are smooth projective varieties. But I mean, just for you to know that actually we could even generalize a little bit more this theorem. Okay, so, I mean, this map that I'm claiming here that exists looks like this. So, it takes divisors on the variety V, and it gives functions from the variety, the points of the variety, to the reals. So basically, those functions that I have here, I don't know if this is clear, this is okay. Those functions that they are here are the height. So basically, this result is telling you that you have a function, and actually given a divisor D here, I'm going to denote this by HBD. Okay? So basically the idea is that we start with our variety V, and now given any divisor on the variety V, we are able to produce a height. Okay? So now, of course, I'm going to state the properties that those heights satisfy. Okay? So let's see it. So I can say it with the following properties. So let me state the properties here. So again, the properties have names. So the first one is normalization. So we have that for all hyperplane 8, we have that the height in Pn associated to the hyperplane for a point P is actually equal up to a constant to the height of the point. Right? So, I mean, this means that somehow we are kind of getting what we expect, right? So, this is the first property. The second property it is called functionality, reality, and says that if we have a morphism of varieties from B to W, so this is a morphism. So I'm going to consider D a divisor on this one, on this variety, D a divisor of W. What I want to do is to relate the height corresponding to the divisor on W to the height on B corresponding to the divisor that is the push forward of the divisor D on B. Okay? And actually we get kind of what we are expecting. Then, as I said, the height corresponding, on B corresponding to the push forward of the divisor T for a point P on B is actually equal to the height on W corresponding to the divisor D for the image of the point. And of course up to constants. Okay? All those constants, well, I mean, I'm going to repeat it later, but actually the nice thing is that all those constants, they depend, of course, on the hyperplane, on Pn, on the morphism phi, on the divisor D, but they don't depend on the point that we are evaluating the height. So this is the same philosophy that we saw in lecture 2 when we proved like the properties for the height in the projective space. So it doesn't depend on the point. This is important thing. Okay? And those constants can be computed explicitly. So those constants, I mean, we saw it also in lecture 2, one of the last theorem before the corollaries that we saw. So, I mean, we computed that constant explicitly. And again, in those cases, it can be explicitly computed. Okay? Very well. So, third property, additivity. So if we take two divisors, D and E, then the height associated to the sum of the two divisors is what you're expecting. So it is the height of the first divisor plus the height on the second divisor up to a constant. Again, a constant that we can compute explicitly. What is it? Here. Fourth property. So, linear equivalence. So, I mean, I guess that this is another property that you were expecting. Like, I mean, if you want a height with nice and good properties, you're kind of expecting that actually the height doesn't depend on the divisor that you take, but only on the class of linear equivalence. Okay? And in this is what we have. If two divisors are equivalent, linear equivalent, then the corresponding heights are equal, of course, up to a constant. But again, this constant doesn't depend on the point P and can be explicitly computed. Okay. 5. Positivity. If D is an effective divisor, so we write it like this, and B is the base locus of the linear system D. So if you want, we can write it like this, or we can write it as the Riemann-Roch space like this. So all those are concepts that we defined in lecture 3, in case you are lost now and you don't know what I'm talking about. So if you don't know what I'm talking about, go back to lecture 3. So you will get all those definitions. Okay, so under these circumstances, so B is an effective divisor and B is the base locus of the corresponding linear system, then for all points in B but not in P, so in this locus, we have that the height in B defined by this divisor is greater or equal than a constant. And again, a constant that can be explicitly computed. 6, there are many properties, many good properties. So this is algebraic equivalence. So again, if you don't know what is algebraic equivalence, go back to lecture 3. So this time we take T, an ample divisor, okay, and E, and a divisor that is algebraically equivalent to 0. Then we have the following, and sorry, I'm going to write it here, very small before moving to the other blackboard. Then we have that the limit when the height of the point goes to infinity of the quotients of the height of the point by the two divisors is equal to 0. So how should be this interpret? That if here D is ample and E is algebraically equivalent to 0. So if E is algebraically equivalent to 0, that this limit goes to 0 actually means that when the height in general goes to infinity, so this one goes to infinity much faster than this one, because here the divisor is algebraically equivalent to 0. So this is how it should be interpreted, this property. Okay, let's go to the other side to see the other properties. I know, many properties. And then you have to prove them. 7, finiteness. So this time we take again an ample divisor, D. We take a finite extension of number fields. We take B fixed. So this time, B, be careful, is going to be a bound, is going to be a rational number. I'm sorry for the notation because we are using B all the time as a bound. So we did it in the theorem, for instance, that we proved in lecture 2. But just 1 minute ago, I denoted by B the set of fixed points for the locus base on the divisor. So please don't get confused by this abuse of notation. So B fixed, then we get the finite result that we were expecting and that we have for heights in projective spaces. That is that the points on the variety defined over that finite extension such that the height is bounded by B is finite. Right? So this is the kind of fineness result that we expected and we already had for the heights in the projective space. Okay, and now 8, and this is the last one. Uniqueness. So actually those heights H, B, D, so they depend on the divisor D that we are fixing, but they are determined up to a constant. So basically the Veil height machinery is telling you that you can construct those heights associated to a divisor and that satisfy all those properties that we stated before. And if you have such a function, such a map that gives you those heights, actually those heights are uniquely determined up to a constant. But again, this is a constant that doesn't depend on the point, okay? And again, they can be explicitly computed. Okay, very well. So I'm going to give you now the proof of this theorem. So, I mean, actually, because of course I want to tell you many things today, so I'm not going to have the time to make the proof for all the properties, but what I'm doing, so proof construction, is that I'm going to tell you how Weil construct explicitly those heights. And then once that you have the explicit construction of those heights, so let's say that this is a difficult part, then you can check that with this explicit construction, all the properties that we listed here, they are satisfied. Okay, so I mean, the checking the properties, this I leave it as an exercise for you. So, I mean, it's a good exercise, actually. So you can check if you are understanding. So, I mean, I'm just telling you the part of the proof of the construction. How do you construct this Weil machine, height machine? So, the idea is as following. So, let's start with a divisor such that the Riemann-Roch space associated to E has no base point. So now I'm going to choose a morphism associated to D. So how do I construct this? So basically, I look at the Riemann-Roch space associated to D. So I take a basis for this vector space. So these bases are functions. And with those functions, I can construct a morphism. So here, n is the dimension of this vector space. Well, sorry, n plus 1, because I have n plus 1 coordinates. So this is the dimension of this vector space. So I produce this morphism that to a point here, I send the evaluation at the base, I mean, at the functions that I took as a base of this space. Okay, so I mean, of course, this morphism depends on the base that I'm taking of this space. Okay, but of course, we're going to see that I mean, it doesn't matter at the end. It doesn't matter the choice that you do of those of the base here, so of those functions, you get the same thing. Okay, so the idea is that you get a morphism like this. Okay, so now that you have a morphism, you can define a height, as we just did before I state this theorem. Right? So we can define the height of a point in the variety as the height corresponding to the image by this morphism of the point in Pn. And then we get the normal height in the projective space. And this is what we do. So we define now the height associated to this divisor at a point equal. So, I mean, this is by definition. So, I mean, this is the Weil height of machinery. This is how we define this. So, we define it as the height in the projective space of the image of the point by the morphism that we took. So, this is the definition. So, now the idea is what happens if D has base points. So, it's not in this situation. Then this is a result that we saw also in lecture 3, that actually we can write then otherwise D can be written as D1 minus D2 with DI with linear system not having base point. So basically, those divisors, D1 and D2 are in this setting. So for them, we can define the height like this. And now, of course, we want linearity, right? I mean, we saw the additivity on the height. So there is now a natural way of defining the height for D. So in this case, what we do is that we define the height on B given by the divisor D on a point P us the difference of the height corresponding to the divisors D1 and D2. So we define it like this. So, yeah, of course, now, so I gave you the construction, I gave you the idea, how you construct those heights, but now, of course, I mean, you have to verify that all those properties are satisfied. But I mean, this really, I leave it as an exercise, but I mean, it's not difficult. Why it is not difficult? Because basically all the properties that we stated, we already proved them for heights on projective spaces. And we are defining here those heights in terms of heights on projective spaces. So basically you have all the properties that you want, okay? So I leave you that as an exercise. And here you have the explicit construction. So remark, I mean, I know that I repeat it several times, but I'm saying it again because I think that is very important when you want to do like explicit computations. I mean, I like examples. I'm going to do an example later, don't worry. I like examples. And again, I repeat it. For me, until I don't see an example, I don't really see the concept. And I really think that being able to do things explicitly, computationally, it's important. There are people that they just like theory, and it's good. Me, I also need the examples. So, remark, I repeat it again. All the constants in the theorem O1 can be explicitly computed. So I insist on this fact. Okay, so now I mean, as always that we give like a strong and deep theorems, now we can get all the corollaries. And we get them more or less for free. So let's start with the first corollary of this theorem. So basically what I'm going to do is to restrict myself to the case of abelian varieties. So an abelian variety is a particular case of a variety. So I mean, I can apply this theorem when I take V an abelian variety. So let's see what it gives. So again, if you don't know what is an abelian variety, go back to lecture 3. Okay, corollary. Let A over K be an abelian variety over a number field. We take a divisor. Let T be a divisor. And M an integer. Then we have the following properties. 1. The height on the abelian variety A associated to the divisor T that we took there, evaluated at M times a point P, is equal to the following: M squared plus M divided by 2. Okay, I write it and then I explain why this is true. So the idea is that on an abelian variety, so we have extra properties. It's a variety in which we have a group law. So we can add points. In particular, we can consider P plus P plus P plus P M times, and then we have the M times P. So we could be interested on related the height associated to a point P and the height associated to a multiple of that point on the abelian variety. And I mean, this equality gives you that. So maybe I think I'm going to state at the same time that I state the, so many times a corollary doesn't need a proof, because it's an easy consequence of a theorem, so there is nothing to say. In this case, maybe I need to say a little bit. So, I mean, at the same time, I'm stating the properties I want to state, I'm going to say something about the proof, like how do you get that, starting from the theorem that we just stated, okay? The veil height machinery. So, basically, the idea, what you have to notice here, so I'm going to see multiplication by m as a morphism, right? I mean, this is the idea. The veil height machinery use morphisms to define different heights. So the idea is that m times a point, you can see it as the image of p by the morphism multiplication by m on the abelian variety. So I can do the push forward of a divisor t. And it was, I erased, but it was one of the first properties that we look at them, right? Well, when we consider it was the second property, actually. And I mean, the idea is that this is equal to this, m squared plus m divided by 2 times c plus m squared minus m divided 2 minus 1 t, right? Why is this true? Because actually multiplication by m is a morphism of degree m squared. So here you have a minus 1, and then this m squared kills this m squared, and you get m divided by 2, m divided by 2, so you get m times c, and you get what you have here. Okay? So you play with you have this equivalence of divisors, and now that you have this equivalence, this linear equivalence on divisors, then you use the thing that the heights are the same up to a constant. And this is precisely what we wrote here. Okay? So property 2, if D is a symmetric divisor, so, I mean, this means this, I recall it. That means that D is equivalent to minus D, where a minus D means the push forward of D by multiplication by minus 1 on the abelian variety. So, if D is symmetric, that means this happens. Then we have that 8 of A D of P plus Q plus this another height is equal to this. Wait, I'm doing it right? Yeah. Twice. So, I mean, this is like a parallelogram equality. And of course, we always have those things up to constant. And so, I mean, this is nice, right? Because you have this height on the abelian variety, you have this group law on the abelian variety, so you want to be able to say something about the height of P plus Q in terms of the height of P and Q. The thing is that you need something else. It's not only the height of P and Q, you also need the height of P minus Q. So you get this, this equality. Again, so what is a morphism that you have to consider here? You have to consider adding P. So this is a morphism on the abelian variety. This is as a variety, not as an abelian variety, because adding P is a translation. So 0 doesn't go to 0. But it still is a morphism as for a variety. So you can consider that morphism, and you use the properties that we saw before, how the height behaves with a morphism, and then you can get this equality. So if you want, what is the idea of the proof here? So here the only thing that you have to notice is that the composition of the height with multiplication by minus 1 is actually equal to the height plus a constant. So you use this plus the properties we saw before, and then you can deduce this. So now there is a third property, but I mean, this is the nice thing about having a blackboard. I'm not going to write it here, the third property. I'm going to reuse what I wrote here. So in this case, what we have is an anti-symmetric. So D, if instead of symmetric, is anti-symmetric. meaning that we don't have exactly this, but with a minus here. Then we have a relation that says that this is equal, you can forget this term, and you get this equality. So how the proof goes in this case, you just have to notice that in this case, these relations get a minus. And then again, if you use, as before, this relation with the properties that we had in the machine height, Weyl height machine, then you can deduce this equality. So I leave you this as an exercise also for you, so you can check the details and that what I'm saying is true. Okay, very good. So now we are going to see another proposition that relates and tell us more information about those heights. And this I'm going to give you the proof. So there are many proofs, so I have to choose which ones I do with all the details. And this one, I'm doing it. So let's go. So again, this is a proposition that is going to relate the height when we consider different divisors. So if we have different divisors, what can we say about the corresponding height associated to those divisors? So, proposition. So, let's see over K be a smooth projective curve. So, I mean, I recall that a curve is a variety of dimension 1. So all this Weyl high machinery that we developed applies also for the particular case of curves, so varieties of dimension 1. So in this case, we have the following. So let T and E be divisors with the only condition that we ask is the degree of D is greater or equal than 1. Okay? Then, in this situation, we have the following. The limit when the height of D of P goes to infinity of the quotient of the two heights is actually equal to the degree of E divided by the degree of D. Why we were expecting this? So, I mean, I'm going to do the proof, okay? So, I mean, you will see the detailed proof why this is true. But, I mean, before going to the proof and saying, okay, it's true, because we are following, like, logical steps. So, let's try to look at the intuition, what is behind this equality. Actually, this is kind of natural, and we were expecting that, right? Why? What is the height of a point associated to a divisor? So we have to look at the Riemann-Roch space of the divisor, right? We are going to get sections of this Riemann-Roch space. We are going to construct the corresponding morphism. And the height of the point, it is just defined at the height of the image of it's equal to the height of the image of this point on the projective space. And we have seen that we have a morphism between projective spaces and the degree is D. Then the height here is equal to the height here multiplied by D, this degree, right? So it is natural to expect that somehow those heights are up to constants equal each of them to the degree of the divisor, so the degree of the induced morphism, times a height in the projective space. And here you have, indeed, the degrees of the corresponding divisors. So, I mean, this equality is quite natural. So you could have guessed it, let's say. Later we're going to see the proof, so this is true, that's all. But I mean, I wanted you to have this motivation. Okay, so this is the first property. And the second one actually is kind of a reformulation of this one, of this first one, but in terms of functions instead of divisors. So this time I take f and g, two functions on the curve. The condition that I ask is that f is non-constant then we have the following. The limit when the height of f of p goes to infinity. So notice that, I mean, this is the height of a number, right? Because it's the image of the function. So the limit of the height of g of p divided by this is equal to the degree of g divided by the degree of f. So, I mean, again, and actually the proof of this second property is straightforward after we prove the first one. What we have to do is we just have to take, for f and g, the corresponding divisors corresponding to the zeros and the poles of f and g, and then apply just this theorem. So we get that those degrees corresponds to those degrees, and those heights corresponds up to constants to those heights. So we get the result. Okay, but let's prove first the first point before saying any more about the second point. Okay, let's prove it. Proof. So some notation. So let me call d equal to the degree of d and e to the degree of e. Okay, the degrees of the divisors. So I'm going to define. So let us consider this another divisor that depends on n, on a parameter, as n times e times the divisor d minus d times the divisor e plus d. Okay, who is the degree of this divisor? So, I mean, this part gives us degree 0, right? Because the degree of d is d, the degree of e is e, so this is ed minus de equal to 0. So basically the degree of an is going to be equal to the degree of d, and is going to be greater or equal than 1 by hypothesis. Okay, so this, and I refer to lecture 3, implies that an is ample. Okay, so we have produced those divisors. So now we can use the positive property of the Weil height machinery to conclude that we have, okay, I erase here, that the height associated to this divisor is bounded below by a constant, right? Okay, so we have the positivity property of the Weil machine gives. So I'm going to put a name to the constant, okay? Maybe a weird name, but you will see why. So this is the constant. So the constant, of course, it doesn't depend on the point, but it may depend, and I'm writing it explicitly, on the divisors d, e, and n. Okay? Okay, and we have here, I mean, I didn't write it, but the variety here is clear, is the curve we started with, and is the height corresponding to this divisor. So we have something like this. But now, because of the linearity, I mean, recall the way in which we brought the divisor an as a combination of the divisors capital D and capital E. So we are going to use that equality and the linearity of the Weil machine. So we can write this as n times E8dP minus this. This is really an equality, not up to constant. Okay? So now we have this expression. So what I'm going to do is to rewrite it in a different way. So I mean, I'm looking at, I have this constant less or equal than this huge expression. So I'm going to divide all this expression by nd hd of p. Okay? So I'm going to do this division and you will see that it's true. And I'm going to put things in a different order. So we get this. So I write it and then I explain. Okay, what did I do? So basically I moved this to the other side, I moved this to the other side, and also these two terms to the other side of the inequality, and I divided everything by nd, the height of p. So if you do this in this inequality, you get this thing, okay? But now there is a funny thing. The funny thing is that actually this is true for all n. So instead of taking n, I can take minus n. And then I get the opposite thing in here. Okay, so now that we have this, so I mean basically this is multiplying by minus 1, what's happening? Okay, so imagine that 8p, because it's the limit that we want to study, goes to infinity. So if hd of p goes to infinity, this goes to 0, because this is a constant. And I'm making this go into infinity. So same thing in here. But now this is still true for all n. So I can take n as big as I want. And if I take n as big as I want, this part also goes to 0, and this part also goes to 0. So this means that all this quantity here goes to 0. And this is what we want, right? This means that the limit, when the height of p goes to infinity, of this quotient is equal to e divided by d. That it was precisely, by definition, the degrees we were looking for. So we have the result. So I mean, this is why a little bit I insisted on the motivation about why this result should be true, because actually the proof then is different from what we get from the intuition. So I mean, I think that it's good to have both things, like the proof, so here we have the proof, and then the intuition behind this result, okay? Intuition is always very good, because intuition is the one that tells you what you have to prove. I mean, when you want to prove like a new result, what you should try to prove. So the intuition tells you, oh, this could be true, so then you try to prove it. Okay, so that was about the first property. So now we can look at the second property, and actually I'm going to leave to you the details, but I mean now the second property is very easy, because as I tell you, you just have to write the divisor associated to the function f as d minus d prime. So those are the zeros and those are the poles. So you decompose in this way the divisor, and then you do the same thing for g, and you call it e minus e prime. So now I can write, I mean, I'm going to use, of course, the first part, and I need something else. I also need that this, we already saw it. Right? So I mean, this is a property. In general, we have this thing, this property, we saw it before and we used it before. So now I'm going to use the first property we proved with this data. So we have that the limit when the height of f of p goes to infinity of this is equal to the limit when the height of p goes to infinity, so not only of f. Recall that D is the divisor associated to f of this quotient. But again, those are constants that don't depend, that don't depend on the point P. So in the limit, they disappear, right? And I mean, this is equal actually to the limit without the constants. But I mean, then I can compute this limit as in here. So this is equal to the degree of E divided by the degree of T. And I mean, this is precisely equal to the degree of G divided the degree of F. And then we have the result. Okay, very well. So now we have, I mean, what we did today. So, I mean, I gave you this Veil height machinery. So now you know how to produce like many heights. But somehow, I mean, it's a bit annoying, if you want, that those heights depend on the divisor, right? Even if they depend up to a constant that can be explicitly computed, but it's like you lose a little bit of control there. So you would like to define something a little bit more canonical, right? And this is what we're going to do. So I'm going to state a theorem by Néron and Tate that give us the definition or the construction of this height that is more canonical. And actually it's going to be called the canonical height. And I mean, this is really the height that we use. Okay, let's go. So, theorem due to Néron and Tate. So let V over K be a smooth variety. Well, of course, a projective variety, even if I'm not writing it. And of course, I'm talking about smooth varieties because it's easier to give all the definitions. And it's the case that we are going to use in practice. But again, if you are interested, you can find in the references that I gave you, like small modifications of these results that also apply for varieties with some singularities. Okay, so we have our smooth variety in this case, defined over a number field, so K is a number field. We take, again, a divisor, we have to. And phi, a morphism from the variety to the variety with the following properties. So such that the push forward of the divisor here by the morphism, so it's again a divisor on B, is linearly equivalent to a multiple of D, the starting divisor, for some alpha greater than 1. I know that this looks like a weird condition, but I mean, you will see later that it's not that weird, that is kind of natural. Okay, so under these conditions, there is a unique function that is called the canonical height on B, of course, relative to phi and D, that we call 8 hat, and that goes from the points on the variety to R, such that, so I mean, I know that the notation starts to be complicated. So now we have this height that depends on the variety, on the morphism, and on the divisor D. But I mean, you will see, that is worth it. So this canonical height, so it is unique and satisfies the following properties. The height on a point is actually the same one that you get with the Veil machinery up to a constant. So basically, if you want the difference with that, is that we are really fixing a height among all the heights that they are well defined up to a constant with the Veil machinery. And this is the extra condition, because if you want, I mean, this is still true, sorry. This is still true for all the heights that the Veil machinery gives you. So I mean, this first condition is still not that strong, but this second condition is the one that is really strong. So what is happening is that you can control the image of the height by the morphism like this. So no constant, really a multiple. So this is why we were looking for that alpha. So I mean, somehow what we are doing is like, so we have some freedom. I mean, this height is not well defined, it's well defined, but I mean, it depends, I mean, you can take up to a constant. So what we are doing is to fix somehow the constant to make a unique choice of that height such that this property is happening. Okay? And well, the nice thing about this definition is that now it only depends on the linear equivalence of D. So, I mean, it doesn't depend anymore explicitly on the divisor. It really only depends on the linear equivalence of the divisor. And this is the nice thing. It can be computed explicitly. Well, you will see the explicitly. So it can be computed explicitly with the following formula. So the canonical height on a point P is equal to the limit. So I mean, this is why the explicit, this is why I was laughing, because this is a formula, but in practice it's difficult to compute because it's a limit. So you have to compute the limit. And it's not easy to compute the limit. So what you compute is an approximation. When n goes to infinity, of 1 divided alpha to the n and the height associated to d of, well, I write it and of the iteration of the image of the point n times. Okay, so this is complicated. So what is the idea? So the idea is that somehow those heights depend on the choice on d up to a constant. So somehow you want to define something that kills the constant, that forgets about the constant. So how is the way of doing that? So the idea is to construct it as a limit, because in a limit somehow we kill the constants if you do quotients by the right things. So how do you do that? How do you do that limit? And I mean, this is in general for a variety, so it's even not an abelian variety. So I cannot do like p plus p plus p or something like this. Actually, this is what we are going to do, I mean, for the phi. We are in the special case of an abelian variety. But in the general case, we cannot do that. So we have to take a morphism. So I mean, this is a natural thing to do, like considering like the image of p by the morphism several times and doing the limit. The problem is that if I do the limit like this is going to go to infinity. Because, I mean, in general, the height is always bigger for the image than for the starting point. In general, you are kind of multiplying by the degree of the morphism you are considering here. So this thing would go to infinity. So this is why the idea here of dividing by something that somehow makes that stable, that limit. And what do I have to put here? So, I mean, this is why the condition that looked a little bit artificial now looks natural. So, I mean, this constant alpha is the thing that I have to divide here to get here something that works well. So, okay, now we are going to see how to prove this. So, basically, what is the idea? Okay, we define the height in this way. So, what we have to prove is that this definition makes sense. And what is the meaning of this definition makes sense? That this limit exists. Because if this limit doesn't exist, then we haven't defined anything. And once that we check that, I mean, this is well defined, then the only thing that we have to prove is that it satisfied the conditions that we have here. Okay? So this is what we are going to do. So let's prove that this is well defined first. Okay, so proof. So again, so we apply the height machinery. So applying the height machinery the part about the linear equivalence, and here we have two divisors that they are linearly equivalent. So those two, we get that there is a constant that I'm going to call C, such that the height of the image of the point, of any point, minus alpha times the height of the point is less or equal than C. Okay? So this is something I'm going to use later. This is the first thing. So now, how I'm going to prove that that limit exists? So I'm going to prove that this sequence, so I can write it like this, V, D, V, N, P, that this sequence converge because it is Cauchy. Well, because it is a Cauchy sequence. So basically the idea is that, I mean, we have defined a height as a limit. So in order to prove that it is well defined, we have to prove that this limit really exists. So it is the limit of a sequence. So we have this sequence. So what we have to prove is that this sequence converges. So what is the idea? I mean, those are real numbers, right? I mean, and the real numbers, they are a complete space. So Cauchy sequences converge. So basically, we just have to prove, in order to prove that this is well defined, that the limit exists, that it is a Cauchy sequence, right? So to prove that it is a Cauchy sequence, what we have to prove is like the difference between two terms. If the n is very big, then it is very small, right? So for that, we have to look at this. So I write it like this. Phi n minus this. Okay, so here I write a term with n, a term with m, and we want to check that when n and m are very big, then this thing is very small, right? This is what we want. So, okay, this is equal. I can rewrite it as follows. So, yeah, you may think that is a weird thing of rewriting things. So I'm going to explain it. I write it and I explain it, why we take it like this. So the idea is that I'm writing it as a telescopic series. P. So what is the idea? I'm considering this sum, but actually for each term, the last term equals the first term. So when you do this sum, you get cancellations of all the intermediate terms, except the last one and the first one. And this is precisely what we have here. Okay, so let's say that this is just a clever way of rewriting this thing. Okay, but now I can use the triangle inequality here for the, now with the absolute value. This is a standard classical absolute value on the reals. So I can use the triangular inequality here to rewrite that as the sum like this. So I put the absolute value here. Okay, tell me if you agree with this. Well, you cannot tell me actually. This is a funny thing. But I mean, as I said, what I did is like, I mean, this bar was here, I was taking the absolute value of this, but I take the triangle inequality and then I get a smaller unequal with this in here. Okay, but now what's happening? What is happening is that actually what I have here exactly looks as the bound that I have here. Right? So I can use it to get that this is a smaller or equal than this sum with the constant, right? So I mean, I just have to get phi of I minus 1 to the p as the point q here, right? So each of those terms, they are smaller or equal than c. And I get this. But now this is something that I know how to compute, right? So this is actually equal to alpha minus m. So I mean, this is a geometric progression. So we have a formula for the sum of the terms. So I get this thing. And now, I mean, this is easy to see. C is a constant. So if m and n goes to 0, this goes to 1 minus 1, so 0. This is also a constant, so this goes to 0. And this is a Cauchy sequence, and it converges, and so the limit exists, and everything is well defined. So we have what we want. Now, for the properties that we have here, actually they just come from the definition, right? Because, I mean, for instance, the second one, so we are proving that this canonical height is equal to alpha, this canonical height. So here is the image, here is the point. But I mean, this is just because of the definition, right? So the canonical height for phi of p gives you here the same thing, but with a +1 here. So I mean, the limit, you get an extra alpha that appears here. So you get it for free. And then, I mean, this condition is because you really define this as a limit, and this is equal to this up to a constant, all the terms in here. So, I mean, once that you prove that this is well defined, then the thing that you have these two properties comes for free. Okay, very good. So, yeah, I said that I was going to give an example. I'm going to give an example, but first, let me do something else. So, I mean, again, this result, this theorem by Néron-Tate, is general for varieties. So now let's see what happens when we look at the special case of abelian varieties. So what can we say? So I'm going to leave the theorem here so we can compare maybe later. And I'm going to state here the result for abelian varieties. And well, I mean, actually the example that I'm going to do later with abelian varieties is going to be with an elliptic curve, because they are the easiest abelian variety that we have. Okay, so if I take B equal to A, an abelian variety, in the theorem by Néron-Tate, so I'm going to take something else. I have to take a morphism. So the morphism 5 that I'm going to take is multiplication by 2. So I mean, this is a good thing about abelian varieties, that we know a lot of morphisms that we can play with. So I'm going to take any symmetric divisor. It doesn't matter. Symmetric divisor. And then alpha, I can just take it equal to 4. Okay? Then the canonical height, as we define it, satisfied the following properties. So this is equal to this. So this is just the first property of the Néron-Tate, up to a constant. This is the first property of the Néron-Tate theorem. So here I just changed the V by an A, so I didn't do anything. Now, the second property, I can rewrite it like this. Nice. This time the morphism is multiplication by m. We have, because on the limit we have the same properties that for the height, so we have a parallelogram equality. So notice that this is the funny thing with this canonical height, that the constant that we had before in this parallelogram expression disappeared. So we really have an equality here. So this is useful for computing height of other points. 4, we can define a pairing. So this is going to be really useful. This you will see it in lecture 5. So in the next lecture that we are going to talk about the Mörder-Weil theorem. And I mean, this is going to be a key piece. A pairing that can be defined when you have a height. So this is a nice ingredient. So we define this pairing as follows. So it's a bit complicated. So I mean, we are kind of using, it's not exactly the parallelogram equality, but it looks a little bit like. So we take this expression, and what is happening is that with this definition, this pairing is bilinear. Nice, you will see how we use it. Of course, this is also a consequence of the previous theorem. It only depends on the linear equivalence of D. And then 6, and this is nice, it is bounded by 0. So, I mean, this is by making the constant explicit. Recall that here we had a constant. We had the positivity of the Weil height. So in general, this is greater or equal than a constant, that depends on many parameters. But actually, and I repeat it many times, this constant is explicit and we can compute it. And in this case, it's 0. 0 is the constant that we have to put. With equality, and this is nice, if and only if the point P is a point of torsion. If P has finite order. So, I mean, this condition is very nice because actually, you recall, we did it. So, we proved that if you have a point on the projective space, then it has height always bigger or equal than 1. But, I mean, be careful, actually that 1 is a 0, right? Because it was 1 for the multiplicative height, and this is the logarithm 1, and the logarithm of 1 is 0. So it's the same thing, okay? It's the same condition that we had here for points on the projective space. And we had equality if and only if, and we prove it, the coordinates were 0 or a root of unity. But what is a root of unity? a root of unity is something, is a number, an algebraic number of order a finite number. So this number at some power is equal to 1. This is exactly the same thing that we get here. So the torsion points are the point at infinity that is playing the role of 0 for the algebraic numbers, or finite order, or really a point that n times p is equal to the point at infinity, is equal to, and this is the same thing that a root of unity to some power gives you 1. So I mean, this is really the analogous thing. So again, this is intuition. The proof is different. The proof is you just compute the explicit constants and you get it. Okay? But again, I'm coming back to the idea that the intuition is very important. Because I mean, by having this on the rationals, right? On the algebraic closure of the rationals, on the algebraic numbers, having this intuition, oh yeah, the height is equal to 1, the multiplicative 1, if and only if the coordinates are 0 or root of unity. Okay, now I want to translate this into varieties, into Abelian varieties. What is equivalence in? So this root of unity are the point of finite order. And then we get the equivalent result. So, okay, now I'm going to the example that I think that you need it. But, I mean, I'm not giving the proof. Well, I mean, I said more or less how to prove it each time, because this is really a consequence of the previous theorem. So, I mean, I just restated for the case of Abelian varieties, for the particular case in which the variety V is an Abelian variety. And now we go to the example. So, let's do this example with an elliptic curve. So, yeah, we are going to do several examples. Well, not today. Today only this one, but in the 5th lecture, no, you will see another nice example with an elliptic curve. So, example, I'm going to get this elliptic curve. Okay, so elliptic curves are the easiest examples of Abelian varieties because they are Abelian varieties of dimension 1. So we have this elliptic curve. So I need to get a symmetric divisor. So easy. This is ample, symmetric and ample. So I'm getting this divisor. Why is this divisor interesting? Actually, because the Riemann-Roch space associated to it, it is that generated, by these functions, right? This is a classical exercise. I mean, I don't know if you have seen it before, but I mean, when you want to prove that all elliptic curves are given by equations like this, actually you prove that by taking this divisor, this Riemann-Roch space has dimension 3, so it has to be generated by 1 and 2 other functions, and then those functions satisfy an equation like this. So, I mean, this is kind of classical. I'm not giving the details. So, what is the funny thing that by taking this basis that I took here, actually the embedding, if you want, that it induces from E to P2, I mean, it's really what we have there, right? So, a point x wide goes to 1 x wide, right? So, I mean, it's a natural embedding. So this means that the height associated to this divisor is just the height on the ambient space of the elliptic curve. So it is just the height on the projective space. So I mean, it's an easy height, let's say, that we know how to compute it. Okay, but then what about the canonical height? So the canonical height on the elliptic curve, so I mean, I'm not writing the divisor because I already wrote it there, so we know who we are talking about, is equal to this limit when n goes to infinity of 2 to the 2n times this. Okay, so I mean, this is a limit, but this limit, of course, is difficult to compute. So we are just going to compute the first terms, okay? So I'm going to take a particular point. So even it is not a rational point, so I'm going to take this point on the elliptic curve. So we may verify that this point is on the elliptic curve. If we make x equal to 2, we get 8 minus 2 equal to 6. So if y is a square root of 6, here we also get a 6. So indeed, this is a point on the elliptic curve. So we have this point. So okay, first I'm going to compute the height of this point, but not the canonical height, the normal height. So I mean, this is just the height on the ambient space. So this is just the height of, I mean, this point as a projective point in here. So I mean, this is just the absolute, the classical absolute value, the maximum of the classical absolute value of the coordinates. So a square root of 6 is greater than 2 because it's 2 point something. So this is the value. So this is equal to, well, log, because it's the logarithmic height, the one that I'm writing down. This is logarithm of a square root of 6. And if you want an approximation of this is equal to this. Okay, so this is only the first term of this limit. So now I'm going to compute the second term to see a little bit what it does. So I compute twice the point. So I compute twice the point, and I get this. So, I mean, you can see, right? I mean, this is the intuition, the feeling that when you start to do 2 times p, 3 times p, 4 times p, 5 times p, then the coordinates get more ugly, if you want, get uglier. And I mean, this is actually that the height is going higher. Okay. So this is a point, and again, the height associated to this is going to be equal to the logarithm of the higher coordinate. So now here you have to be a little bit careful, because I mean, when you take the absolute value, you get here the maximum of the absolute values of the coordinates, is because you took the coordinates to, so you remove the denominators, so you have integers on the field extension that you are, but then you want the coordinates to be coprime. And here, as I brought it here, it is not coprime. Why? Because 2 divides this, 2 divides this, and a square root of 2 divides this. So actually, I have to divide everything by a square root of 2, right? So then the biggest one actually is this one, but divided by a square root of 2. So I compute, and I get that this is equal to the logarithm of 300 divided by a square root of 2. And, well, actually, this is not really what I want, but I have to divide by the right thing. So I'm going to divide this by 4. So I'm going to divide this by 4. And then I get more or less something like this. So, I mean, as you see, the convergence is not that fast. I mean, those two numbers, they are not close to each other. And I mean, you could keep going with this to see what is the canonical height, but I mean, as you see, it's not easy. You have to compute many terms. And actually, this is a computational problem. Like, I mean, of course, now this is implemented, so in many programs, so you don't have to do it by hand, as I'm doing it right now. So, I mean, again, I invite you to check what is this value with magma. So, I mean, this we cannot do it by hand, because we cannot compute this limit by hand. Like, it would mean like to do what I'm doing here, like computing for each multiple and to see how much it converges. So again, with magma, you have different commands. So you have naive height. So this just gives you the height on the x coordinate inside the projective space. So this is not that good. But then you can compute the one that I told you on lecture 2. So you can compute that one, and this one is the height when you look at the point on the projective space. So I mean, this is the case. This is the one that we are computing. So with this, you can compute this height for p, for 2p, so the values that I'm giving to you here. And then you can use this one. So simply, well, I'm going to call it p again, simply height, and this one gives you the canonical height. So with magma, with this command, you can compute the canonical height, where of course, because again this limit is difficult to compute, what you are computing is an approximation. So what magma does is that actually computes like many terms of this sequencing until some point, and even you can ask about the precision. Like, tell me 3 digits, decimal digits that are correct. But you're not going to get the exact value. But well, you get like a good enough approximation. So you can do all this with the computer. Okay, so with this I'm done for today. So this is the end of this exercise. I hope you enjoyed. Again, I invite you to ask me questions if you have them. So let's try to interact a little bit, even if it is via the chat and not really in person. Another time will be. And see you in lecture 5. Thank you very much. Bye.